This is the video lecture over section 8.1, which the book calls a single population mean using the normal distribution. From our perspective, though, it would be better to say that this is the section about finding a confidence interval for a population mean when the population standard deviation is given. This is the first of the three scenarios that we mentioned in the previous video. We're going to quickly review how we find a confidence interval by hand, but then we're going to move on to using the calculator to get the confidence interval and let our focus be on the interpretation, what the result actually means. So here's how you find a confidence interval for a population mean when the population standard deviation is known. First, you need to have a simple random sample. And if you don't know that the population is normal, then you're going to need a sample size large enough to be able to invoke the central limit theorem. So your sample size will have to be at least 30. Because the technique we're using here requires a normal distribution, we have to be sure that the means are normally distributed. So either the population has to be normal or your sample size has to be greater than or equal to 30. Once you've got your sample, you're going to calculate your sample mean x bar, and you're going to calculate sigma sub x bar, and you'll notice that I gave it a special name here. I called it the standard error. This is a common name for sigma sub x bar. We didn't really need it before, but it makes it easier to describe the process here, so I threw the name in. Sigma sub x bar is called the standard error. We can calculate x bar because we have a simple random sample, so we just take all the data from the sample, add it all up, divide, and we get our sample mean. We can calculate the standard error because we're assuming that we know sigma, and we also know n because we chose the size of the sample. So we can get both of those. Once you've got your sample mean and standard error calculated, you get to choose a confidence level. Now in a textbook problem, we won't be allowed to make this choice, but in real life, you just get to choose how confident you want to be. And we talked about this a little bit in the last video. There's a balance between accuracy and precision. You might choose to make your confidence level really high, but then your interval gets really wide and it's not very useful. So then you might choose a different confidence level based on that. In a textbook problem, on a quiz question, on an exam question, you will not actually choose the confidence level. It will be chosen for you. So we'll just use the given confidence level. And perhaps I should have said this before, but in a textbook problem, in a quiz problem, in a book problem, you won't actually be gathering a sample. I'm not going to send you to the store to buy 36 bags of M&Ms just so you can do a problem. The sample has already been gathered, and either the sample mean will be given or we'll have to use the data to come up with the sample mean, but you won't actually go out and get a sample. I know you love this course, but I'm sure you're not that dedicated to statistics that you're going to go out and get bags of candy or measure alligators. One of our examples in this video is going to be to measure alligators. I'm not going to put you in harm's way just to learn a little bit of statistics. The sample's already been gathered. Sorry about that tangent there. Last step, we're going to calculate the bounds of the interval by adding and subtracting the appropriate multiple of the standard error to and from the sample mean. I know that step might sound confusing, but based on the confidence level, we know we have to go a certain number of standard deviations away from the mean. We just find that standard error and then add and subtract that number of standard errors to and from the mean to get our bounds. This is exactly what we did in the one example from the previous video. Let me remind you here. We had a random sample of 36 fun bags of M&Ms and we were told the mean count. Again, on the previous slide I said gather our simple random sample. But in a classroom problem, you're given the sample data or you're given some statistic from the sample data. If we assume to know that the population standard deviation is 3 pieces, we know sigma, that's part of our assumptions. Construct a 95% confidence interval for the mean number of M&Ms in all fun size bags. We were given the confidence level. In real life, you get to choose it, but in a classroom problem, it's given to you. So here we were told to use 95% confidence. So in the second step, we were told to calculate the standard error, and we did that in our problem. We found the standard error by doing sigma divided by the square root of n. We knew sigma was 3. We know n is 36, so we took the square root of 36. 3 divided by the square root of 36 is 3/6, and we reduced that to 1/2. The last step says to calculate the bounds of the interval by adding and subtracting the appropriate multiple of the standard error to and from the sample mean. We took the sample mean and we subtracted 2 standard deviations and we added 2 standard deviations. And that's because we wanted 95% confidence. That's the appropriate number of standard deviations. And that's how we got our bounds. And then we wrote up an interpretation, which we'll get into in a minute. But that's how these steps work. Rewording this for our classroom setting. we're going to identify the sample mean, or we're going to take the sample data if it's given and put it into the calculator. We'll have to verify that either the population is normal or that the sample size is at least 30. Second, we identify the sample mean if it's given, and also identify the pieces of the standard error. If the sample mean isn't given and all we have is the sample data, then we'll calculate it by running the calculator function 1var_stats. We will identify the confidence level because it will be given. Notice that all we're doing is picking things out. We're identifying them. We don't actually have to do these things. We just have to take them from the problem. And then we'll calculate the bounds of the interval by using a calculator function. Instead of doing all that number crunching by hand, we're going to run a calculator function that will do all of that for us and spit out the interval. Our responsibility will be to identify that it's appropriate to use the calculator function, run it correctly, and then interpret the result. We're going to write up a sentence interpretation each time that we do this. The calculator function we use for our scenario is called ZInterval. ZInterval is the calculator function you want to use when you need a confidence interval for a population mean and the population standard deviation is given in the problem. Now the calculator still has to do the mathematical steps that we outlined in the previous slides. So the calculator is going to need to know x bar, and it's going to need to know the pieces of the standard error, which we said are sigma and n. So the calculator will ask us for sigma, x bar, and n, and then it also needs to know the appropriate number of standard errors to jump from the sample mean, and so we have to tell the calculator the confidence level, and it'll prompt us for that too. So ZInterval will have 4 inputs: sigma, the population standard deviation, x bar, the sample mean, n, the sample size, and the confidence level. When you put those 4 things into the calculator and run the function, the output will be the confidence interval that we're looking for. For our first example, let's redo the problem that we just reviewed from the previous video. A random sample of 36 fun-sized bags of M&Ms yields a mean count of 32.5 pieces of candy per bag. If we assume to know that the population standard deviation is 3 pieces, construct a 95% confidence interval for the mean number of M&Ms in all fun-sized bags. So let's start with the goal of the problem. We're being asked to construct a confidence interval. And more than that, it's a confidence interval for a mean, which is the first part of the description of what ZInterval does. It finds confidence intervals for means. But notice you have to be in the case where the population standard deviation is known, so we need to make sure that we know the population standard deviation, and you can see it specifically says that the population standard deviation is 3 pieces. So we're talking about the scenario that ZInterval handles. Before we just jump into ZInterval though, remember that we have to know that we've got a normal population or have a big enough sample size. The calculator function does not verify that. We have to verify that. So either the population has to be normal or the sample size has to be at least 30. But of course the condition is met because we've done this problem before. The sample size is 36 and that's why we get to assume normality. The central limit theorem saves the day here. If you don't have a large enough sample size and you can't verify that the population is normal, then it's inappropriate to use ZInterval because ZInterval uses a normal distribution in its analysis, just like we did when we did this problem before. That's an assumption that ZInterval makes, so you have to verify that assumption. Here we're good because the sample size is bigger than 30. Going back to our steps, we don't have to calculate the sample mean because it was given. We don't have to calculate the standard error because the calculator function is going to do that. We don't need to choose a confidence level. We just have to identify it. It was 95%. We're ready to calculate the bounds, but we're going to do this with the calculator function. The calculator function we're going to use is called ZInterval, and to access it, you press the stat key and then scroll to the tests option, which you can get to by scrolling once to the left. And you'll notice choice 7 is ZInterval. So I'm going to push the 7 key because I'm too lazy to scroll down there. And whether you're using a TI-83 or a TI-84, your input screen should look the same as long as we're all in the same input mode. There are 2 input modes, data and stats. You use the data mode when you have a list of data, and you use the stats mode when you're given the statistics. In our example, we were given the sample mean, and we were given the sample size. We weren't given the raw data, so we want to be in stats mode. And that'll be the mode that we use in all of the examples today. To make sure that your calculator is in stats mode, push the right arrow and then hit the enter key to select the stats option. Notice that the calculator asks for the 4 inputs we mentioned before: sigma, x bar, n, and the confidence level. Let's go back through the problem and identify each of those. Sigma was 3. The population standard deviation is 3 pieces. X bar, sample mean, was 32.5. The sample size was 36. That's how we knew that the central limit theorem was in play. And the confidence level is 95%. So what the calculator is going to do is it's going to take sigma and divide it by the square root of n to get the standard error. It's then going to figure out how many standard deviations you have to go in a normal distribution to get 95% of the data. And then it's going to add and subtract that number of standard errors to and from the sample mean and come up with our interval. Scroll down to sigma, type in 3. X bar was 32.5. N was 36. The confidence level was 95%. You can see my calculator function was already set for that. You just type 0.95. Scroll down to calculate, hit enter, and we get this interval that ranges from 31.52 to 33.48. You'll notice the calculator uses the nerdy interval notation that you might remember from algebra. Now we write an interpretation. Recall that our confidence level was 95%, so we could say we are, or if you don't want to be part of the group, you can say I am 95% confident. What is it that we're estimating? Well, it was a mean. That the mean what? Make sure you describe what it is. It's the mean number of M&Ms. And now here I like to emphasize that it was for all fun-size bags, because I think it's important to remind everyone that we're finding an estimate for the entire population. However, if you didn't use that word all, it still says the same thing. When you say in fun-size bags, the implication is that you mean all fun-size bags. But I like to emphasize all. Annoyingly, I capitalize it and I underline it. You don't need to put any kind of extra emphasis on the word all, but I like to do that because it's a reminder to the class that we're estimating the mean for all fun-size bags using only a sample of 36. Getting back to what our answer means, we're saying that we're 95% confident that the mean is between these two bounds, and so that's how we finish it. Is between 31.52 and 33.48. Sometimes it's appropriate to put units on the end, like you might say between 31.52 and 33.48 candies or M&Ms. Here I don't think that's necessary. So I would just end like this. This is a standard interpretation of a confidence interval. You brag about how sure you are that you're right. You talk about what it is that you're estimating. Right now we're estimating mean, but later we'll be estimating a different parameter. So you got to say what this is. Without the word mean, this interpretation is actually incorrect. If we say we are 95% confident that the number of M&Ms in all bags is between those, that's certainly false. We're not able to say that every bag has between 31.52 and 33.48 pieces of candy. We're only able to say that the mean for all bags is between those. So that word mean is important, and without it, your interpretation is incorrect. It's not just poorly worded, it's flat out wrong without that word in there. You have to say what it is you're finding the mean of. The mean number of M&Ms in all fun-size bags. It makes a difference. It matters that we're talking about fun-size bags, and it matters that we're talking about M&Ms, so you need to be specific. And then, of course, you have to say what the interval is. And notice that I don't write interval notation around this. I'm writing this in standard language, so you just write out the two numbers with the word and in between them. Now, if you're remembering back to the example we did by hand, you might recall that these aren't the bounds that we came up with. Our bounds were 31.5 and 33.5, so why did the calculator give us a slightly different answer? Well, it's because the two standard deviations that we jumped when we did it by hand was an approximation from the empirical rule. The empirical rule tells you that you get approximately 95% of the data if you go two standard deviations away from the mean. You actually get a little more than 95% of the data when you go that far. So to get 95% of the data, you only want to go about 1.96 standard deviations away from the mean, and the calculator did that. It didn't go a full 2 standard deviations away from the mean. it went a little less than 2 standard deviations away, and that's why we got a slightly tighter interval than we had before. The calculator's answer is better because it uses a more exact number of standard deviations. The beautiful thing is that we don't really have to worry about that when we're using the calculator. We trust the calculator to get the right number of standard deviations. This will be especially handy when we're talking about something that the empirical rule can't handle, like in our next example. We have 3 main jobs when we're doing these problems with technology. We have to verify that the assumptions are met. We have to identify the inputs to the technology that we're using. In our case, that's the calculator. And then we have to interpret the results. That's important. Anybody could put these numbers in, but it's important to know what it means. I want you to think of it like you're the expert. You're the nerd down in the nerdery crunching all the numbers for your idiot boss, and you want to explain it to that person so that they can understand what the answer means. You want to write your interpretation in a way that somebody that knows very little statistics could still understand. I think we're ready to try another example. Here's that alligator example that I teased earlier. A random sample of 10 alligators from a specific swamp yields a mean length of 8.1 feet. Assuming the population is normally distributed with a standard deviation sigma of 0.9 feet, construct a 99% confidence interval for the mean length of all alligators in the swamp. Okay, approaching it from scratch. We're being asked to find a confidence interval for a mean. That's good because that's what ZInterval does. ZInterval finds a confidence interval for a mean. But there are still 2 more things we have to verify before we can use ZInterval. One is that sigma has to be known. The calculator is going to specifically prompt you for the value of sigma, the population standard deviation. Do we know the population standard deviation? Yes, it says to assume the population has a standard deviation of sigma equals 0.9 feet. So sigma is known. That's good. The other thing that you have to verify is that the sample means are normally distributed. That was one of the steps that we talked about in general. Either the population has to be normal or the sample size has to be greater than or equal to 30. We have a really small sample size here. Our sample size is only 10 alligators. But that's okay. We don't need the central limit theorem here because we're told the variable is normally distributed. That's a pretty safe assumption. Things like the lengths of organisms, heights, weights, those tend to be normally distributed. So that assumption isn't a really big leap. Assuming to know the population standard deviation can be a big leap. Like, why would you expect to know that here? Maybe you have some data from another swamp or something like that. But that's a pretty big jump. But assuming that the population is normal is not exactly a leap of faith here. Either way, you don't have to worry about that in a textbook problem. If they tell you to assume the population is normal, and if they tell you that you know the population standard deviation, just run with it. This is definitely a Z-interval problem because we are finding a confidence interval for a mean given the population standard deviation, and we have a reason to suspect that the sample means are normally distributed because the population is normally distributed. Z-interval requires 4 inputs, sigma, x bar, n, and a confidence level. You just have to pick those out from the problem. We already identified sigma. When we were determining that this was a Z-interval problem, we said that sigma was 0.9. X bar is the sample mean, and it says that the 10 alligators in our sample yielded a mean length of 8.1 feet, so X bar is 8.1. N, we already talked about, was 10. That was too small to invoke the central limit theorem, but we were covered by the fact that the population is normal. And the confidence level is 99%, and this is what I was talking about before. A confidence level of 99% is not something that the empirical rule can handle. The empirical rule can do 95% and 99.7%, but not 99%. Before technology was prevalent, you would just look up the number of standard deviations in a table. For 99%, it was a certain number of standard deviations. You would just look that up. With technology, that's no longer necessary. We can just tell the technology what the confidence level is, and it will determine the appropriate number of standard deviations. So let's run these inputs in the calculator. To access Z-interval, it's stat, scroll to tests, and choice 7, Z-interval. You're already in stats mode if you switched from last time. You won't have to constantly pick that option. It'll stay there unless you actively change it or your batteries die or something. Sigma was 0.9. X bar was 8.1. The sample size was only 10. And the confidence level now is 99%. We scroll down to calculate and hit enter. Actually, before I do that, let me remind you what the calculator is going to do. It's going to take sigma and divide it by the square root of n, so 0.9 divided by the square root of 10. It finds the standard error. It then determines the number of standard deviations you have to go in a normal distribution to get 99% of the area, and it multiplies that number of standard deviations by the standard error. It then adds and subtracts that number to and from the sample mean in order to get the bounds of the interval, just like we did when we did it by hand in the previous video. We get this interval that ranges from 7.3669 to 8.8331. I don't want you rounding these bounds because these have already been rounded. If you round too liberally, then you're changing the confidence level because you might make the interval tighter or wider than it's supposed to be. So please write out all of the places that the calculator gives you. Now we write up our interpretation, and again, I've got kind of a formulaic way to do it. First, we brag about how sure we are that we're right. So we are 99% confident. We're very, very sure of our estimate this time. What are we confident about? Well, we're confident about our estimate of this mean. So that the mean. The mean what? Don't say the mean alligator. I want to know what variable it is that we estimated here. We're estimating the mean length. The mean length of what? Of alligators, but it's all alligators, and so I'm going to brag about it. I guess I need to be careful though. It's not literally all alligators, it's just the ones in this swamp. And I think it's important to include this extra little part here. It would be misleading to say that the mean length of all alligators in general would be modeled by this data, because all of the alligators that we used in this example came from the same swamp. So that's really all we're able to estimate here. And what are we 99% confident about? That mean is between these two bounds. Is between 7.3669 and 8.8331. And here's an example where I think it would be a good idea to include the units. Are these numbers in inches? Are these alligators tiny? Or are they in meters? Are these alligators monsters? Well, these are measured in feet. And I think it's important to say that. So again, let's break down our interpretation. We bragged about how sure we are that we're right. We mentioned the parameter that we were estimating, which is a mean. We talked about the variable that we were estimating, the length. We talked about the population, all alligators in this swamp. You don't need the word all, but I like to emphasize that this is an estimate for all of them. We don't even know how many alligators are in this swamp. But we still have an estimate that we're 99% sure is right as long as all of our assumptions are satisfied. And then of course you have to tell me what the interval is. We think it's between these two bounds. Now a 99% confidence level is pretty big, and that's why we have a fairly wide interval. Our interval is 1.5 feet wide. Considering that our sample mean was 8 feet, an error of 0.75 feet in each direction might be considered to be a lot. If so, we would just back off the confidence level. We could drop that down to 90% confidence or 95% confidence and get a tighter interval. Those are the kinds of things that people consider in the real world. You don't need to worry about that in our class. We're just going to do whatever we're told to do. We were asked for a 99% confidence interval. That's what we're going to give them. Let's try another one. A random sample of 42 dental implants yields a mean cost of $4,500. Let's assume the standard deviation for all such procedures is $1,000. Construct a 90% confidence interval for the mean cost of all dental implants. This is a confidence interval for a mean, and that's what ZInterval does, but in order to use ZInterval, we have to know the standard deviation of the population. Thinking of it from the perspective of the calculator, that's the first input we need to have, is the population standard deviation. In the previous example, it was obvious because it used the symbol sigma. In the example from the previous video, it used the phrase population standard deviation, so those were clear. It says that we are assuming we know the standard deviation for all such procedures. If it's the standard deviation for all of them, then that's a population standard deviation. So this is a confidence interval for a mean with the standard deviation of the population. This is a Z-interval problem. Z-interval is going to ask us for 4 inputs: sigma, x bar, n, and the confidence level. And if you're worried about having those memorized, don't fret. The calculator is going to prompt you for them. Suppose you identify this as a Z-interval problem, but you don't really know what to look for to plug into the calculator. Well, just bring the calculator function up. Stat, scroll to tests, choice 7. It will tell you, hey, I need sigma, x bar, n, and c level. Suppose you didn't even get that far and you just know that it's a confidence interval for a mean, and you're wondering if Z-interval is appropriate, but you can't remember what else you need to know. The calculator prompts you for sigma. It says, hey, you better know the population standard deviation or else you can't use me. The one thing the calculator will not prompt you for is to make sure that you know that the sampling distribution of sample means is normal. In the previous example, that was easy because we were told the population was normal. Here, we're not told anything about a normal distribution. So are we stuck? Can we not use Z-interval? We're still good because of the central limit theorem. N is 42. That's large enough to satisfy the central limit theorem. That's greater than or equal to 30. So we're good. We just have to identify each of these values in the problem. Sigma is the population standard deviation. We already identified that. That's $1,000. X bar is the mean of the sample. It says this random sample yields a mean of $4,500. So X bar is 4,500. N is 42. We identified that when we saw that the central limit theorem applied. And here we were told to use a 90% confidence level. 90% is another one of those values that we can't really estimate with the empirical rule, so it's good that we have the calculator. You might notice that that's the lowest confidence level we've used so far. Confidence levels can be as low as you want, but you want to be fairly sure that you're right. So the lowest one that I ever use in my examples is 90%. And why did I choose 90% here? Maybe you don't care, but we have a really large standard deviation here, and so the hops are going to be fairly big. So to balance this accuracy precision issue, I chose a smaller confidence level to compensate for the large standard deviation. Again, that balancing act isn't something you really need to worry about because you're just going to do what you're told in the problems. But this is the kind of thing that you have to worry about in the real world. If you choose a confidence level that's too big when you have a really big standard deviation, then your interval winds up being too wide. Again, not a concern for you, so I apologize for rambling, but I think that part's neat, so I can't help but talk about it. Let's bring up the calculator function again. Again, it tells you what it needs. Sigma is 1,000. X bar was 4,500. N was 42. The confidence level is 90%, so that's 0.9. Calculate. We get this interval that ranges from 4,246.2 to 4,753.8. So you can see that the width of this interval is around $500, because if you subtract these two numbers, that's about $500. It's a little more than 500. The margin of error is half of that. So we've got a margin of error of about $250. That might sound like a lot, but I didn't want to make my confidence level too low and sacrifice how sure we are that we were right. So I had to sacrifice some of my precision for accuracy. Now we write our interpretation. Maybe you should pause the video and see if you can do it on your own. If you don't care to, here we go. First we say how sure we are that we're right. We are 90% confident, which is the lowest confidence we've had so far. But we're still pretty sure that we're right. 90% confident is pretty confident. We're still quite likely to be right. Confident about what? Well, our estimate in this mean. That the mean what? What were we estimating? Well, it was a mean cost. Mean cost of what? Well, let's just go back to the problem. I'm really just copying this wording here. The mean cost of all dental implants. I'm going to capitalize and underline the all because I'm obnoxious. But otherwise, I'm copying the wording from the problem. Sometimes it comes out a little bit clunky, but I'm not looking for Shakespeare here. As long as you get the point across, I'm okay. And what are we 90% sure about? That mean is between these two bounds. Now here the units are dollars, so I feel compelled to put the dollar signs in front. I also am going to put those place-holding zeros that we typically write in the hundredths place for money. There would be nothing wrong with not writing the dollar signs and instead writing dollars on the end like we did with the feet in the previous example. It's just more customary to put the dollar signs. And this is a sentence, so I guess I should put a period at the end. So again, breaking down our interpretation, we start by saying how sure we are that we're right. We make sure to mention that it's a mean. If I take that word out, this sentence is false. We are not 90% confident that the cost of all dental implants is between these two bounds. There are some dental implants that will be more expensive than that. If you live in an area of the United States with a higher cost of living, you're not going to be able to get a dental implant for $4,000. It's going to be significantly more expensive. Or if you have a lot of issues, if you have to pay for an extraction and for bone grafting and all these other issues, that's going to drive the cost up. So there's no way that all dental implants cost between these. But that's not what we estimated. The reason why this sentence is wrong is because we were estimating the mean cost. That word mean is important. It's not just there for show. Put the variable in there, the cost. Put the population in there. This is the cost of dental implants. You want to make sure you explain what it is you're estimating the mean cost of. Right, this is the mean cost of dental implants, not heart implants, which would be way more expensive, or restaurant sodas, which seem to be approaching these costs. I don't know why I have to pay $4 for a glass of soda, but whatever, we can talk about that later. We're estimating the mean cost of dental implants. And then, of course, tell me what the interval is. Between what? I want to know where you think that mean is. Okay, let's just knock out one more. A large online retailer implements a new procedure for their deliveries. A random sample of 200 deliveries that use the new procedure yields a mean delivery time of 2.68 days. If we assume that sigma equals 1.5 days, construct a 95% confidence interval for the mean delivery time using the new procedure. Okay, so we're being asked to find a confidence interval for a mean. Hopefully this is a z-interval problem because we don't know how to do anything else. What makes a problem a z-interval problem? It's got to be a confidence interval for a mean where you know the population standard deviation, and you also have to be reasonably sure that the sampling distribution of sample means is normal. We were given the population standard deviation. It specifically says that sigma equals 1.5. Sigma is the symbol for the population standard deviation. And we have a sample size of 200, which is way more than what we need for the central limit theorem. So this is a z-interval problem. And when you're using z-interval, there are 4 inputs. You need to know sigma, x bar, n, and the confidence level. I encourage you to pause the video here and see if you can pick those 4 things out. Okay, maybe that wasn't the hardest task because we had already underlined 2 of these things, but it's still worth your practice. Sigma is 1.5. X bar is 2.68. That is the mean of the 200 in the sample, 2.68. N is 200. And the confidence level is 95%. Let me bore you one more time with what the calculator is going to do. It's going to take 1.5 and divide it by the square root of 200 to get the standard error. It's then going to say, okay, you want a confidence level of 95%? That's about 1.96 standard deviations. Remember, the empirical rule says that it's about 2. It's closer to 1.96. It's then going to take the standard error that it calculated and multiply by 1.96 or so, and then add and subtract that number from the sample mean, and that's how it comes up with the interval. Okay, let's get this confidence interval. Stat, scroll to tests, choice 7. Our population standard deviation was 1.5. X bar is 2.68. N was 200. And we want a 95% confidence level. We calculate, and we get an interval that ranges from 2.4721 to 2.8879. You'll notice this time we got a much tighter interval. The difference between the upper bound and the lower bound is 0.4 days, which means that our margin of error is half of that, which is 0.2 days. 1/5 of a day is less than 5 hours. So we've got this thing nailed down to a margin of error of about 5 hours, and we're 95% sure that we're right. Why is our interval so small? Well, we had a fairly small standard deviation to begin with, 1.5, and then our sample size was enormous. It was 200. The square root of 200 is around 14. It's a little bit bigger than 14. And so this sigma got divided by around 14, and we wound up with a very small standard error. So when we hop those 2 standard deviations away, we wound up with a very small margin of error. And that's why we have such a tight interval. Let me start with that Mad Lib style interpretation that I keep writing, but then we're going to take this a little bit further, which I'm sure you're super excited about because you can't wait to hear me ramble even more. But again, let's start with what I want you to be able to write. First, tell me how sure you are that we're right. We are 95% confident. We're 95% confident about what? About our estimate in this parameter, and the parameter is the mean. Again, let's just start stealing some wording from the problem. The mean delivery time. That the mean delivery time using the new procedure, just stealing the wording. You'll notice that I didn't use the word all because in my opinion it would sound kind of funny to try to throw it in there. The mean delivery time using the new procedure for all delivery, that doesn't sound very good. So while I like to put in the word all, please understand that I don't always put in the word all because sometimes it sounds funny. I'm trying to get the point across, but I'm not going to sacrifice what I think is clear right just to try to make that point. So this is good enough. The mean delivery time using the new procedure. I guess if I wanted to make it clear that it was all of them, I could wedge the word population into the front, the population mean delivery time. I don't like that because I pretend like I'm writing this for people who don't know statistics, and writing in population mean would not help them at all. Anyway, we're 95% confident that this mean delivery time using the new procedure is between these two bounds. Okay, so this is the cookie cutter style interpretation I want you to be able to write. But I just want to take a moment to talk about the kinds of things that we could answer with a confidence interval like this. All right, this online retailer has implemented a new procedure, presumably because they want to make the delivery time faster. Maybe they want to make it cheaper, but let's suppose that they were trying to do this to make it faster for them. And suppose that in the past, their mean delivery time was 3 days. Well, according to the confidence interval, we're 95% sure that the mean is between 2.4721 days and 2.8879 days. 3 isn't on this interval. We're pretty sure that it's less than 3. We're 95% sure that it's on this interval. So we're very, very sure that it's less than 3 because 3 isn't on the interval. So almost certainly they've reduced the delivery time to under 3 days. That's an extra step of analysis that you can do with these confidence intervals. For now, I want you focusing on writing our style of interpretation. So if you need help writing these interpretations or you need help identifying these as ZInterval problems, get a hold of me, find me in an office hour, send me an email, make sure you understand.